So, welcome to In-Memory Full Text Search with Kotlin. I hope you're having a lovely day or night or wherever you are in the world. My name is Kshitij. For those wondering, the K is silent and the T is soft. I'm a software engineer currently living in New Delhi, India, and I work as a backend developer at Upcover. I do native Android as a hobby. I started when I was in college and basically kept going. All right. Now, before we start the talk, I think I'm sure you must have a question on your mind. We're talking about in-memory full text search. So why? Why care about in-memory full text search? Why care about in-memory search at all? Well, the easiest answer is it's usually the fastest way to present a search experience to your users. It's much faster than making an API call to your backend. Snappier search interfaces, snappier queries is equal to happier users. So that's the motivation behind this talk. And then finally, before we start, let's talk a little bit about the structure. So there are going to be two colors of slides in here. One is with a dark blue background. Imagine that's the audience talking to me. And then the white color background is when I'm talking to the audience. It's going to consist of an open monologue, which is an oxymoron, I hope. And then I'm going to have a bunch of Conan O'Brien and maybe some F1 references. All right, let's start. Situation: you're building a podcast app, as I'm sure most people are these days. Your server sent you a list of 500 episodes of a podcast. Each episode contains a title and lengthy show notes. You want to allow your users to search the episodes quickly and thoroughly. What do? Well, of course, one answer is quite obvious, right? You build a naive search interface. For example, for every query the user enters, you search the entire catalog of episodes, and then for every episode, you match the search query with the title and show notes, or whatever data you have in your instance. I'm going to continue to use the mockup I have on the right of a podcast app that I made in like 5 minutes. So forgive the rough edges around it. All right, so let's explore the naive search idea a little bit more. Imagine you have a podcast episode model as a data class. It has an ID, a title, and show notes. Of course, real world data can be more complex, but for the purposes of this talk and for keeping it simple, we're just going to assume that we have just these three properties in an episode. Now, imagine that you have a data source that can return episodes to you. In this instance, I'm simplifying it down to a synchronous call. Of course, real world use cases would be much more complex. And then my final assumption is that you have a search box somewhere which allows you to register a callback that gives you the query whenever the user enters some text. We're going to look at how we process this query in the naive search implementation. Of course, what you could do is on the episodes list that you had, you could run a filter and you could match the query against both properties of your episode. And then finally, once you have some search results, you could show them to the user. Notice that this particular search variant is quite, well, let's say it's inadept. We are basically searching if the query is a substring of either the title or the show note in our episode. This, this works, but there's a few problems in there. First of all, it's quite slow. For every search query you get, you have to run it through the entire list of episodes that you have, which in our case is 500, if I remember correctly. And then for every episode, you have to match two pieces of text, and then it's going to be slow. Yeah. Secondly, perhaps a bigger issue is that it's inaccurate. You have limited options to check if a string matches your query or not. And then finally, there's also no way to, order results on the basis of their relevance. As an example, if you search for the word Obama in this hypothetical podcasting app, you might not get any results at all. However, if you enter the query with the correct case, you'll actually get the correct search results. But even then, the search results are not ordered in the order of their relevance. You're getting an irrelevant search result first, and the actual ones you need later. So what do we do about this? Naive search doesn't seem to be cutting it. You probably don't want to present this experience to your users. How can we improve this? here comes full text search. This is where full text search comes in. Now, full text search lets you look at all the words in every stored document to match a search criteria. This is sort of an informal definition of full text search. If you're wondering what a document is anything that contains some sort of text. In our case, we're working with a podcast app. So for us, a document is an episode of a podcast because an episode contains two pieces of texts. One is a title and other is the show notes. Right. So it's faster, it's more accurate, and much more flexible than naive search. It's it's actually a pretty great topic to explore on your own once you're done with this talk. I highly recommend everyone look at it. All right, but how does it work though? How does full text search work? How is it able to achieve all of those features? How is it implemented? The magic of full text search lies in this data structure known as an inverted index. It's what powers it, and we are going to explore what the inverted index is, how do we build one, and how do we actually use it. So an inverted index contains information of every word stored in every single document. It's called as an inverted index because instead of storing which document contains what text, like a usual index would, an inverted index actually stores what piece of text is present in which document. If you were to look at it as a simple data structure, imagine a map. An inverted index would not be something that maps an episode to the data inside that episode. It would actually match the data inside an episode to the list of episodes it's present in. And if this sounds confusing, just bear with me. We'll go through what this looks like in much more detail. Now, you need to build an inverted index before you can use it. And unfortunately, building the inverted index is sort of an expensive process. But think of it as a trade off. You spend some time in the beginning building the index, which dramatically speeds up your search queries later. On top of that, you can do some clever text processing that allows the index to find search results more accurately. Now, as if that wasn't enough, some clever data structures allow the index to be very memory efficient too. Things like Radix tries, things like Patricia tries. And it goes even further than that. Even cleverer text analysis allows the index to rank search results effectively. The gist is inverted index is sort of like magic. But we'll look behind that magic and we'll see how it's actually built. So, how do we build the index? Well, I'm going to walk you through a series of steps. Eventually, we'll have a full text search index ready for us, and then we'll also learn how to use it. So, the first step of that process is text extraction. In formal terms, I think it's known as information retrieval. Information retrieval, it's actually a field of study that many people pursue. It's a fascinating topic. For the purposes of this talk, I'll keep it very simple. Um, I'm just going to assume that we have a podcast episode like this. Uh, as a quick side note, this is one of my favorite episodes of this particular podcast. I highly recommend you check it out once you're done with the talk. All right, so imagine an episode has a title, which in this instance is Down to the Kakaru, and then there's two paragraphs of show notes in there. So how do we extract the text from it? Well, I'm assuming that we still have our list of episodes from our data source that we had earlier. Now what we're going to do is we're going to build a map, and that map's keys are going to be episodes, and the values are going to be the pieces of texts inside every single episode. Just want to preface this by saying this is not our full text search index. We're in the process of building one. Now what we can do is we can loop over each episode in our list, extract the text from it, and then put it back in our map. Uh, Notice how we actually extract the text though. We're just building a single string. Inside that string, first we add the show's title, and then we also add the show's notes, which is in this instance, the title is Down to the Kakaru, and then the show notes are a couple of paragraphs. So essentially, you will end up with an episode that has just a single string associated with it inside the map. Once you've done this for every single episode, you'll essentially end up with a massive list of strings, right? Uh, Inside which every string actually contains the title and the description for every single podcast episode. So now we're done with text extraction. Let's move on to the next step, which is Processing the text. Here's a problem, right? Users don't really search for sentences, they search for words. Even if they enter a single word, they expect relevant search results back. In this sense, it is more sensible to break the input text into words or tokens. The advantage here is tokens can be indexed by the inverted index, but they contain some noise and they must be clean before indexing. For example, in the figure on the right, you see that it's a single sentence that's broken up into a bunch of different words, and most of it is fine. But you also notice that there's some noise in there. For example, there's some punctuation marks. There are some compound words. For example, the 7-month word in there, and then some words are uppercase, some words are lowercase, and a bunch of stuff is going on. So we probably need to clean up all of these tokens before we actually add them to our index. We're going to look at a simple example in this case. We're going to work with a sentence called Rashida sits down to talk with Conan. What we're going to do is we're going to build another map, and this map is going to map an episode to the list of tokens it contains. What we'll do is we'll loop over all the episode data that we had corrected in the previous step. We'll split the text we extracted from every document on a white space, and then we're going to put that list of tokens back into the map. Now, this is a pretty naive implementation. This process is technically known as tokenization. And you can, in a real world app, you'll probably not just split on a single white space. You might split on a tab space, you might split on a new line or a series of white spaces. All right, once you've broken down that sentence into a list of tokens, you'll get, for example, in this instance, 7 words on the right. Rashida sits down with Conan to talk. All right. We can probably add another enhancement here though. Rather than just to split the words, we could also lowercase them first. So if the user enters basically this allows the user to enter case insensitive queries. So if they enter Rashida with a small r, they'll still get the correct search results back. All right. Now that we're done with the process of processing text, which by the way can be much longer and much more intensive than what I've just showed here, let's move on to the next step. This is known as reducing text. Formally, we call this stemming. Stemming is the process of reducing a word down to its core. Let's take a look at it in more detail. Now, users don't always enter exact search queries. If they search for the word sit, they usually expect to see the result for sits and sitting too. How do we fix this problem though? We use a technique known as stemming. Stemming helps reduce a piece of text to its original core. For example, in the paragraph on the right, most of the words are fine, but some words have highlighted orange sections at the end. These are sections we could probably do without. So that, for example, if a user searches for the word realizes instead of the exact word realized, we would still present them with the correct search result. So we need to stem our text before we can actually add it to the index. This process, fortunately, I'm not going to cover in too much detail over here. I'll be very honest with you folks. Now, imagine I have a function called stem, which takes in a token, stems it, and then returns it. There's probably some complex stemming logic in there. We'll go over it in the next step. What we're going to do is we're going to take our map that contained every episode by the list of tokens it had. We're going to map the values of that data structure, and then essentially for every token that we had extracted for our episode, we're going to stem in the token, and then we're going to store this new list back inside that map. Now, how do we actually implement the function stem though? There are a lot of popular stemming algorithms already out there. One of them is called as the Porter stemming algorithm. There's a bunch of others. One other prominent algorithm is known as snowball stemmer. But the point is, these algorithms have pre-existing open source implementations available for you. We don't need to get into the complex logic of stemming here. You can add them as a dependency and then you can use them in your project. Now that we're done with the boring part, the processing text part, we get to do the fun part, build in the index. Now, as a recap, I'll remind you what we've accomplished so far. First, we've extracted the string text, string data from every single podcast episode. We have converted that piece of data into tokens for every single episode. And on those tokens, we have applied stemming. So now we have a map that contains episodes as keys and the list of processed tokens as values. So now we can finally use them to build the FTS index, the full text search index. Whew, this code looks slightly complicated. Now we're going to go through it step by step. First, let's take a look at the index variable. It has a complicated looking type, but let's take a look at it in more detail. First, it's a mutable map. Essentially, it's a map that you can modify. Modify as in you can actually put some stuff into it once you have constructed it. The keys are strings, and those strings in our instance represent the tokens that we extracted from every podcast episode earlier. And then for each string key, we have a value of the list of episodes it's contained in. So this map, just like an inverted index, will map pieces of data to the documents that that data is contained in. And we initially just set it to an empty map. Now, next, what we're going to do is we're going to iterate over the map that we had built earlier. Uh, I'll remind you that it stored episodes as keys and their list of processed tokens as values. So what we'll do is we'll iterate over every entry, and for every episode's tokens, we'll map those tokens and essentially build a list of all those episodes where the token is contained. Now, once this is done, you'll essentially end up with an inverted index. And in that inverted index, you'll have keys as tokens, and every key will be mapped to a list of episodes it's contained in. Whew. Now this is done. Here comes the last part, and I swear it's the last part, searching the index. Now we're going to take a look at how we search the index using our existing search box that we had created earlier. I'm still going to assume that we have an on-query callback that provides us with a query every time the user enters something. The first step that we need to do is actually process the query itself. We have processed the documents, but we also need to process the query so as to ensure that the query can accurately map against our tokens. What we simply do is we lowercase the query to make it case insensitive. We split it on a white space, and then we stem every single fragment that we just split. This gives us a bunch of query fragments that we can use, or query tokens that we can use to find search results. Once you've tokenized the query, it's time to actually use them. So what we'll do is, for every query token that we extract, we will find the list of documents that that token is contained in. We can do this because of the inverted index that we built earlier. Here's a neat trick. I'm also using the map not null function available in Kotlin's standard library. Essentially, what this will do is it will eliminate any tokens that do not produce any results. So essentially, I do not need to worry about null results after this point. But here's another complication. So you see every token contains a list of episodes it's mapped against. So after this map not null call, I will end up not with a list of documents. I will actually end up with a list of documents. So that's where the next flatten part comes in. What it'll do is it'll combine the multiple nested lists into a single list, and then the distinct by operator after it. It will make sure that I've removed any duplicate results. Once this is done, you have your search results ready for you. And then in the background there, you can see the faint show results function that you can use to show the results to your user. And you're done. You built an inverted index. You process user search queries. You got some search results, and then you show them to the user. I know you're wondering that, yeah, that was really cool. And I'm not going to lie to you. It was cool. It was really cool. But yeah, I agree. It's complicated. FTS is not a trivial thing to implement, especially not when you have to use it across multiple projects. So I do agree that it is complicated, unfortunately. Yeah, I see your point. I can put this in a library. It would be reusable by every other developer as well. So okay, let's do this. So world meet Lucilla. Lucilla is a fast and efficient, customizable, in-memory full-text search library for Kotlin. It builds a memory-efficient FTS index with a customizable processing pipeline. It also allows you to rank your search results with a dead simple and concise API. The URL for the library is available on your screen right now, but it'll also be present at the end of the talk, so you don't need to note this down. Feel free to check it out. I think it's a pretty cool project, and maybe if it's useful to you, consider starting it. And community contributions are always welcome. Now, that shameless plug out of the way, let's move on to the topic of full text search again. What about ranking the search results? You got your search results back from your index, but how do you determine which search result is the most relevant to your query? Well, the answer for it is not as clear cut as everything I've told you so far. There are multiple scoring systems that you can use to actually rank the relevance of your search result. Levenstein distance, that's a very fancy looking word, but it's not that complicated. Levenstein distance basically compares the similarity between two pieces of strings, and it essentially allows you to determine how similar is one string to another. You could use this to rank your search results. Another industry standard scoring system is called TF-IDF. It's known as the term frequency inverse document frequency score, which is what is actually used in Lucida. It's an interesting topic. However, the details of it are outside the scope of this talk, unfortunately. Now, another question is why not use SQLite's built-in full-text search? That's another great question. Unfortunately, um, SQLite is not suitable for trivial or ephemeral data. Basically, if you have a response coming back from your API that's not supposed to be persisted to your database, it would be a massive pain to actually set up a SQLite table for storing it, creating an FTS index on top of it, and then also maintaining that index. And as this is pretty clear that it's also much more complicated than building an in-memory full text search index. All right. Now, what else can we do with FTS actually? There's FTS is actually a very good ground to build upon. There is a lot of advanced things that you can do with it, including fuzzy searching, boosting specific fields of your documents, some rich querying capability, as well as concurrent text processing. Now, what's fuzzy searching though? Fuzzy searching allows you to match with inexact search queries entered by the user, misspellings, or maybe different variations of a word, and things like that. So, fuzzy searching is all of these features that I'm showing you on the screen right now. They are missing in Lucida for now, but they are planned to be added later. Or a field boosts allow you to mark one specific field of your document as more important than others. For example, in the podcast episodes, if you want to make sure that the title gets a higher priority for matching compared to the show notes, you would use a field boost for it. Richer querying capability allows you to actually specify a more complex query. For example, if the user search query contains, let's say, two words, you can actually do an exact match on those two words. What you can also do is you can search for those two words independently in the inverted index. And then the question of how do you combine the results of those two words depends on what combinator you are using. So richer querying capability is one thing that could be built upon top of this. And then finally, concurrent text processing. As I mentioned earlier in the talk, building an FTS index is an expensive process. It's best done on a background thread, but we could also potentially speed it up quite a bit by processing multiple documents in parallel. Coroutines and channels and a bunch of other concurrency stuff that Kotlin has is an excellent candidate for this. With that being said, that's all, folks. I hope you learned a lot. I hope in-memory full text search is useful to you in your projects. Please feel free to check out the library and any of my socials that you can see on the screen right now. But that's it, and thank you for attending. If anyone has any questions, let me go through the questions in the search box first. Right. How does it rank the search results? Well, ranking search results depends on which scoring system you're using. Um, the specifics of it depend, as I said, on the scoring system. Levenstein distance is pretty good. TF-IDF is the industry standard, so I would highly recommend checking out how does that work. Maybe it's a topic for a future talk. I'll keep this in mind. Now I have a few other questions as well. Shalom, do you want me to? How do you want me to do this?
Oh, yeah. I mean, we can continue with the questions, or if everybody wants to take another minute to just write down any questions you have, vote if you haven't voted yet. That way, everybody can gather their thoughts. Kshitij, how do you feel about your talk? How do you feel that went?
Oh man, it I'm not gonna lie, I was pretty nervous while I was giving it. Kind of still feel my hand shaking a little bit, but I think I'll get over it.
Nice, nice. Yeah, that's. I feel like that's a very common feeling. I remember my first talk. I gave like a but not as big as yours. I mean, I think you've had like you have 78 people here right now. My first talk was like a room of like 15 people, in in Boston, and it's like you put so much work, and like the whole time your whole body's just like shaking, but like people can't see it. It's like the whole thing you're trembling, and man, but you did amazing.
Thank you very
Thank
much. Thank you.
you. If you feel, I guess we're actually seeing quite a few questions pop in, so
Yeah.
let's give it another minute because some of them haven't been voted on. So that's a good sign. People are enjoying are like preparing questions for you. That's a sign of a good talk. That like multiple people are coming up with questions. A common sign of when you're like you try to give a good talk and like it really kind of not a lot of people caught on to what you were saying is like there's those few really nice people who will put like a lot of thought into, okay, I need to ask a question because I can't leave this area blank. Um, and then you get the answer and you're like,
Thank you.
okay, I'll quiet up now. If everybody is finished voting, I will let Kshitij choose. Yeah, you choose which questions you want to answer, and I'm going to show them on stage.
Right. So let's start with the first one, the one that has most votes. What approaches exist for weighting or giving a score to the search result? Right. This is a good question, and the answer for it is actually as varied as yeah. There's a lot of systems that you can use to actually score your search results. Two systems I mentioned in the talk itself. I think TF-IDF, the term frequency, inverse document frequency, is the most common system used for scoring results. If you want to get into more details about it, please enter a message into the chat, and I'll be sure to explain it a little bit before I end. Um, right. I think the next question is, how heavy is it usually on memory? All right. So there's no simple answer to this, unfortunately, because memory in modern computers works a lot differently than we actually think it does. But a good indicator is essentially whatever documents you are putting into the index, assume that it'll be about twice as much as the memory of the original documents itself. So basically, you're storing two copies of your documents, right? One in the original data that you received from, let's say, your API, and then another copy inside the index. While the index itself is quite memory efficient, it makes sure that it only occupies as much memory as is strictly required, maybe 1.7 times the memory of the original data would be the total memory of your total memory usage. Maybe that's a good formula to calculate it. But as I said, memory should not really be a concern when you're building an in-memory full text search experience. In-memory full text search is maybe used for a few hundred documents at max. I have tested Lucila with 1 million documents. Lucila consumed about 500 megabytes of memory for 1 million documents. So it's not as much memory as you think. And when you're usually working locally, it's much a smaller number of documents. So I don't think memory should be an issue in this instance. All right. I hope that answers your question. I think the next question is I think we can remove the stemming part if we combine it into a trie data structure. I'm glad you brought this up. So you can get rid of stemming completely if you don't want it. And as for the trie data structure, that's exactly what Lucida uses in the background. So not only does it use an actual trie, it uses a very optimized version of a trie known as a radix tree, or more commonly known as a Patricia trie. A Patricia trie basically compresses all the nodes of a trie that only have single fields or single children. So it's very memory efficient. It usually consumes less memory than the original set of documents that you had. So it's yeah, that's a good point. All right. I think let's move on to the next question. Why the name Lucila? I love this question. I am glad that you're the only one who brought this up. So first, I think the more the actual the one reason is there's an industry standard full text search framework known as Apache Lucene. However, Apache Lucene is more of a server-side framework. It's more at home for indexing millions of documents in a permanent database. Maybe you've heard of products like Elasticsearch. So essentially, Apache Lucene is the industry standard for all this stuff. Lucilla sounds similar to it. As for how did I come up with the word Lucilla, I'm a fan of F1, and there is a great F1 driver named Sebastian Vettel. I'm not sure if you're familiar with him, but he gave the name Lucilla to his 2020 Ferrari, and I love that name. That's why I gave my library the same name as well. All right. Can we use ML to optimize FTS? Um, I wish I had the expertise to answer this question. I am not a data scientist or a machine learning engineer, so I have very limited knowledge on this topic. But as far as I understand it, you can do a bunch of query pre-processing using machine learning algorithms, maybe. Or maybe you can use ML to get rid of the tokens that you don't really need inside a document. So you can probably improve the FTS pipeline using ML. But as I said, I'm not really the best person to ask this question. Let's move on to the next one. How about using Jaro-Winker similarity instead of Levenstein or for a fuzzy search? I mean, sure, you could do that. As I said, the what I plan to do is Lucilla is eventually going to have a configurable scoring system. So while TF-IDF is the one used inside it by default for now, eventually you'll be able to supply it with different implementations of scoring systems. So if you want Jaro-Winkler, feel free to go for it, man. Definitely. All right. The next question. If I have SQLite anyway for offline functionality, how does SQLite FTS query performance compare to Lucilla? Right. So if you have a massive data set, I think SQLite should be faster because SQLite is just more efficient at all that stuff. But for, let's say, a few hundred to a few thousand documents, in-memory full text search will be much faster because there is no disk I/O involved in there. And Lucilla is already pretty efficient at storing indexes. So it depends on the number of documents you have. If you have a lot of documents, consider using SQLite, or maybe consider not using in-memory full text search or on-device full text search at all. Consider using a backend API instead. But if you have a relatively fewer number of documents, go for it. Go for in-memory FTS; it'll be faster. All right. Any plan to have a Flutter library? Oh, cross-platform request already coming in. Uh, all right. I'll look into it, but I can't give you any promises or any guarantees right now.
All right. Done it all. Okay. Do you have any last words?
Yeah, I think somebody just said, dang, missed most of it. Ryan, I think Shalom ensured me that talks get uploaded to YouTube, so maybe you'll be able to catch up on it later on. And I know a couple of people who are here because this is my first talk as well. Devesh, if you're still in there, I really appreciate you hanging in there. And yeah, a bunch of people basically helped me prepare for this talk, so really grateful for that.
Okay. Okay. Well, congratulations.
Thank you.
It's a live clap, so not emoji. There we are. Yeah. All right. If you want to if you want to answer some more questions or continue talking about it, you can go into the lounge reception, whatever the hell Ermi chose to call it, area where there are tables, and you can just chat with people more. All right. Well, Kshitij, thank you so much, folks. See you soon.
Thank you very much. Bye.